Thank you very much. This is a joint work with my colleagues. It's India National Labs and our collaborators, Patrick Coles and Norbert Lutkenhaus in University of Waterloo. And actually, we independently came with the same approach as was presented in the previous talk. So it's essentially very similar scheme, but we have our own unique perspective on it, but of course there will be some overlap with previous talk. So our motivation for doing this work is that coherent state CV-QKD can achieve secure key distribution with relatively modest technological resources, more modest than with DV-QKD. And this approach is especially appealing because it can be combined with integrated photonic implementation, something which would be the next step in development of quantum key distribution and quantum communication in general. However, conventional CV-QKD protocols require transmission of a local oscillator, which is a high-intensity coherent pulse between Alice and Bob, so they will have a shared reference frame. And this requirement for transmission of a local oscillator is a major obstacle to the implementation of CV-QKD, and mainly for two reasons. So one is security issues. There exist proposals for side channel attacks, which would exploit detection using publicly shared local oscillator. And additionally, there are technological issues. If you need to transmit a local oscillator with your signal pulse, you need first to multiplex them together, then on the Alice side, and then multiplex them on the Bob side, and this involves a lot of operations. Combination of time division multiplexing, wavelength division multiplexing, and polarization encoding. So our main perspective is to move QKD to integrated photonics. And when we started to look how we would implement CV-QKD on the chip, we immediately observed that using local oscillator would be extremely difficult. There will be a lot of components which are not natural to integrated photonics, which needs to be used for multiplexing and polarization encoding. So what would happen if you would not need to transmit local oscillator? Turns out that actually your hardware requirements would be so much simpler. So this was our main motivation. So what we have done independently and similarly to the previous talk, we developed a new protocol that eliminates the transmission of local oscillator. We call this self-reference CV-QKD. And there are three main advantages. First, hardware simplification of hardware requirements on Alice's and Bob's stations. Of course, you don't need anymore the assumption that local oscillator needs to be trusted. And implementation of this approach is compatible with integrated photonics platform. So how it works, you have Alice prepares coherent state signal pulse using Gaussian variation, the same approach as usual. But in addition to the signal pulse, she also sends coherent state reference pulse with a known fixed amplitude. And in each round, Bob performs homodyne measurement on one of the quadratures of the received signal pulse, once again the same as in the standard approach. And he also performs heterodyne measurement of both quadratures of the reference pulse. Or alternatively, you can use twin reference pulses and perform homodyne measurements Q on one pulse and P on the other pulse. And the key operation in this approach is to estimate the phase difference theta between Alice's and Bob's reference frames. So there is this pretty simple geometric relationship between Alice and Bob reference frame, and since Bob knows Q and P for the reference pulse both in his frame and also in the Alice's frame, he can estimate this angle. So theta is the actual angle which accumulates due to the propagation of the pulse, and theta hat is the estimation of this angle. So in reality, of course, there will be additional uncertainty, and estimation will be different from the actual pulse. And the main contribution, should I say, most fundamental contribution is the quantum uncertainty in the reference pulse. So reference pulse is much weaker than would be local oscillator, and we cannot neglect quantum uncertainty in the reference pulse. And so if you do the math, standardly you would have the density matrix which represents the shared state between Alice and Bob. It's just effect, this E is the effect of the channel, some Gaussian or lossy noisy channel on the original squeezed vacuum state. And because we perform this additional operation on recovering the phase, Alice and Bob, they need to align the phases, and because estimation of theta is not the same as theta, this alignment will be mismatched. And we need to average over the distributions of random variables theta and phi. So it turns out that effect of this quantum uncertainty is only on off-diagonal elements of the covariance matrix. So if you look at QA squared or QB squared, those wouldn't be affected. But for example, QA, QB, expectation value of QA, QB, or expectation value of PA, PB, they will be affected. And essentially, they will be different from the standard result by the multiplication by this additional term, which is average value of the cosine of phi. And how it enters into the asymptotic Q rate is through this parameter xi, So essentially, in order to estimate Q rate, we need to know what to have an estimation on this parameter. And it turns out that if distribution of this random variable phi has some natural properties, it's symmetric and tight, xi is tightly bound from the, bound by average of phi squared, and this is just the variance of the estimated theta value. And we can analytically derive this value. And second term depends on whether we use single reference pulse with heterodyne detection or twin reference pulses with twin reference pulse with homodyne detection. So in the first case, delta will be 1, because in heterodyne detection you introduce additional unit of noise, and in the second case it will be 0. And essentially you see that this term is inversely proportional to the amplitude of the reference pulse. So taking this into account, we can analytically compute expected secure key rates. Specifically, this plot shows asymptotic key rates for the collective attacks, and this dashed black line corresponds to the standard case with local oscillator, and colored lines correspond to our approach with a different number of photons in the reference pulse. And as you see, as the reference pulse becomes stronger and stronger, you asymptotically approach the key rate for the standard scheme with local oscillator. So some of us are experimentalists, not me personally, and they did this proof of principle experiment to demonstrate that this approach would work. It was a pretty simple experiment, actually tabletop with almost zero transmission distance, and for simplicity, the same laser was used for both Alice and Bob, which is a little bit of cheating, but we just wanted to see how it will work before we go to the chip. So you see that we essentially characterized the performance of the central component of this approach, signal reconstruction through compensation of the drifting phase. And you see on this plot that phase space is a representation of the reconstructed signal after phase drift compensation, and also performing proof of principle demonstration. And the plot on the right shows expected key rates for current experimental setup with different values of reconciliation efficiency. So to summarize, this new approach, which we call self-referenced CV-QKD, obviates key assumption of standard security proofs, specifically that local oscillator is trusted, and therefore it's more secure implementation of CV-QKD. Second, this approach is manifestly compatible with chip-scale implementation, since it only relies on some simple classical components which are easily to implement on a photonic chip. And as you hear from the previous talks, our experiment and experiments by other groups establish that this approach is a practical one which can be implemented and provide significant simplification of hardware. So we started with this idea of having a photonic chip transceiver for QKD, and having this new approach, which does not require local oscillator transmission, allowed us to design this photonic chip, and a few months ago it was actually manufactured, and it's currently under characterization and investigation. So just a few references, and thank you very much for your attention.
Thank you very much. Time for one question. Yes?
What type of modulation did you use? Gaussian?
Yes, everything assumed to be Gaussian, yes.
Okay, great. Let's thank Constantin again.